processes more automated and economical while creating a safe and comfortable environment for the building's occupants. We will begin with the smart HVAC systems. An HVAC system typically consumes around 40% of total building consumption and 70% of base building. The typical HVAC end-use breakdown is presented in the figure shown here. These numbers lead us to seriously reflect on smart HVAC systems as an alternative to standard HVAC systems. A smart HVAC uses wireless technology to communicate with other smart systems and sensors that record parameters like motion and temperature and adjust the system accordingly. At the heart of a smart HVAC system is a smart thermostat that registers changes in weather, temperature, and humidity in different spaces. Smart vents will help permit or limit airflows in certain areas to even out the temperature. When smart devices like humidifiers and purifiers are added to the system, the air quality in the space is significantly improved. However, what makes this smart system energy efficient is the fact that it's possible to optimize the amount of conditioned air based on data collection using sensors for CO2 levels, for example, or occupancy and temperature. With the help of recent advancements in data storage and cloud computing, building operators receive performance data in real time and fine-tune the HVAC controls accordingly, thereby avoiding wasted HVAC usage. Here is an example of a CO2 level sensor. It's called the NDIR sensor. CO2 level sensors monitor and detect the presence of carbon dioxide based on the absorption of infrared light at a specific wavelength. An NDIR sensor comprises an infrared source, a light tube, a bandpass filter, and a detector. Another example of sensors is the occupancy sensor. It's another key element in optimizing the amount of conditioned air in multi-zone systems. As we can see here, for example, in the room with high load, where we have 2 PCs and 2 people, the VAV box is fully open, while in the room with moderate load, it's partially open. It can be like a program to cycle back or shut off completely when the corresponding space is vacant. We will now talk about the plug loads. A plug load is the amount of energy drawn by a device plugged into an electric outlet. Compared to other building loads, plug loads barely make up for 8% of primary energy consumption in buildings. But as HVAC and lighting systems become more efficient, plug loads represent a growing proportion of total building energy use. Since they are not for base building use, but are rather brought into the building by tenants, their energy consumption is closely related to occupant behavior. We have automatically controlled receptacles that are known as smart plugs. They easily replace existing receptacles and communicate with a controller such as a timer or occupancy switch. The fact that we can monitor and manage plug loads and make them remotely turn off based on feedback from occupancy sensors located in tenant spaces is how we can reduce our energy consumption. We will now move on to lighting. Installing LED luminaires and connecting sensors and control to a centralized management system with data analytics and learning capacity might save up to 90% of energy in fully integrated smart lighting systems. Another smart technology is, Aya, can you move to the next slide, please? Thank you. Another smart technology is window shading. This is an example of passive glass technology. According to variations in light, photochromic glass emits variable quantities of light into the building. It changes color in response to changes in external temperature, allowing or blocking solar heat from entering the building. The Raven Window 2.0 is an example of a thermochromic smart window. We will now talk about distributed energy resources. Distributed energy resources refer to technologies that produce power without relying on the utility grid, such as combustion turbines, fuel cells, and solar PVs. As a result, they can function as standalone systems or as grid-connected systems in parallel with the electric power grid. Cogeneration is an example of a distributed energy resource. It's a method of, as we already know, it's a method of supplementing building HVAC and water heating with waste heat from power generation.
Hello, I'm Aya. I'm now going to discuss the advantages of smart buildings. One of the main advantages of smart buildings is the efficiency in the consumption of energy. Energy consumption in buildings is a major factor that affects the total electricity and the energy used and the associated greenhouse gas emissions. So integrated technologies such as the Internet of Things, IoT, buildings management systems, BMS, and artificial intelligence, AI, would lead to huge reductions in energy costs and would create an environment that reduces energy waste. Another advantage is the reduction of operating and maintenance costs. IoT sensors integrated in these systems can detect the building performance, which can predict the equipment's performance and prevent further frequent replacement of the used equipment. Also, this would reduce the cost of having regular manual service checks. A third advantage is that data collection and visualization. Measuring the cost and the amount of energy used can lead to better decisions for business owners and investors. Increased work efficiency while improving the lighting, indoor ventilation, and air quality of the area would significantly impact the performance of employers. And also security enhancement. Smart security is a system integrated within the smart building and could have a controlled access over the areas of the building using devices such as cameras, smart door locks, security alarms, panels, and much more. This system would ensure the security of the building and could alarm the residents of any unusual activity via email, phone call, or text. Okay. Now I'm going to discuss about what barriers might be preventing building owners or investors to adopt to smart buildings. First point is that there is not enough knowledge about smart building technologies because the smart technologies are accelerating in a very fast pace, and these building owners or investors are finding it hard to keep track of. Second is the lack of funding in the area of energy improvements, especially if we need to replace the full building infrastructure to build a new one with these smart technologies. And the third one is the increasing concern over cybersecurity and safety while using systems such as IoT, but this could be resolved by having IT and operational technology focusing on the solutions on how to control and minimize cybersecurity threats and cyber attacks. The current state of smart buildings. I'm going to talk about how COVID-19 virus impacted the energy efficiency sector and what were the factors that affect the building sector after the COVID-19 pandemic or during it. First of all, we have the shift in energy demand. As we all know, that the use of commercial buildings has decreased drastically due to the work from home situation, and vice versa, the energy consumption in the residential areas has significantly increased. Also, we have restrictive access to the commercial and residential properties. So contractors and site workers would have difficulties accessing the sites for maintenance or for technical problems. And the third factor would be the increase of energy used from energy-intensive subsectors, and the activity in commercial buildings resulted in more energy intensity per unit of activity. We're going to talk about the activity and structural impact. We can see in these charts that at the left we have the time spent at home, and to the right we have the visitors to workplaces and the average time spent at home versus the workplaces. So the demand of electricity increases, the energy consumed by the residential ventilation systems increased. For example, the energy used for the heating system in Europe reached to 40% higher than the electricity consumption in March and early April in the beginning of the COVID crisis. On the contrary, the commercial buildings have seen a significant decline in their energy use since most offices were not operating or opening for a limited hours of the day. And after the spread of COVID-19 virus, knowing that it is an airborne virus, companies now are focusing on the integration of the HVAC systems using IoT technologies, and the increasing demand for smart systems would be to help protect the people's health, enhance building efficiency while reducing costs. Technical efficiency impact, we have negative impact on the energy efficiency funding in buildings in the long term, delay in the installation of efficient smart ventilation systems and other integrated systems due to social distancing. So this led to for professional equipment installers to start offering online consultation for users as a solution for the ongoing problem. And here we can see how the smart buildings can adapt to the new normal, which means during COVID and hopefully after COVID. We can see from the picture how they created a targeted sanitation and surface disinfection strategy with equipment and IoT sensors, managing energy performance by offsetting new HVAC guidelines, optimizing the cash flow through tailored financing solution, monitoring the office occupancy for density and safe distancing, and much more solutions. Also, we have new features and sensors in smart homes. Many companies such as Microsoft, Twitter, and Square are thinking of implementing work from home as a long-term policy. And the increasing need for comfortable and more efficient environment increases the demand on IoT devices such as lighting, smart speakers, HVAC sensors, and etc. New sensors and new features to their devices to facilitate work from home. For example, a mobile application called Symptom Checker is made to check the current health status of each participant, and this app is integrated with a smart home system using Alexa. Other mobile app, other company developed an application that can detect COVID-19 symptoms using voice signals. Third point is the new energy management solutions. Because smart energy management systems are being employed in many houses. For example, Echo devices are a new feature in Alexa device to remind the users of their energy consumption and keep them aware of it. And also Google Nest Thermostat is a smart thermostat by Google that launched an energy saving feature called Savings Finders. Smart lights and smart thermostats could achieve a much more comfortable workspace for the user. And these technologies would really promote work from home experience and increase the rates of work from home jobs. That's why we need the integration of the new smart HVAC systems in the smart buildings. Physical distancing is one of our major problems nowadays, which asks for the need to use smart heating, cooling, and ventilation systems in indoor spaces. So to obtain a healthy and safe environment, many companies have already started using IoT and new investments in thermal imaging technologies and space monitoring analytics have been further studies. Some procedures were implemented, such as night ventilation of workspaces, UV light ventilation, and keeping indoor air fresh. Yeah. Also, we have visitor management. Occupancy tracking is required in smart building. Thermal cameras and temperature sensors are installed to check for the fever of the employers. And for crowded places such as malls, hospitals, universities, QR code-based contact tracing is used frequently. Facility cleaning in commercial buildings. So to ensure efficient and effective disinfection for indoor places, companies are using robots to frequently disinfect used surfaces such as door handles, elevator buttons, and switches. And another example is UVD robots that is a mobile-based and works on a map to check the patient's room that need immediate disinfection, and it's used mostly in hospitals. Here we can see the integration of the smart system technologies as a whole, using the integrated HVAC system, smart meters, on-site generation, LEDs, integrated BMS, EV charging, all integrated and connected with the grid and with the renewable energies used. Okay, so Ahmed.
Okay, so now we'll talk about the different technologies used in smart buildings. First, there is nanotechnology. The U.S. National Nanotechnology Initiative defines nanotechnology as the understanding and control of matter at dimensions of roughly 1 to 100 nanometers. Nanotechnology opens possibilities for more advanced materials that would not be possible with our current knowledge of matter in the industry. One application of nanotechnology for buildings is in insulation materials. An example of this is aerogel, which gives an R value of 10 per inch, which is double of that of polystyrene, which gives an R value of 5 per inch. Next slide, please. Oya. Okay, so there are currently two different forms of aerogel insulation. The first is silica aerogels, and the second is granular aerogel. An example used in the industry now is a panel manufactured by Calwal, utilizing aerogel technology from a producer called Cabot. Calwal's panels can provide a U value of up to 0.05. Okay, so here's the diagram of the insulation panel used by Calwal. The fourth layer has the translucent insulation of granular silica aerogel, and it has a thermal insulation of up to 0.05 U value. Next. Okay, now responsive materials and systems. Architects and engineers define a smart system or material as a product that can respond to outside stimulants with a certain level of intelligence. The first type is a responsive material that changes its properties in response to a broad array of external stimuli. The second type is a transduction system that converts energy from one form to another. Okay, so the first example is photochromic paint. Photochromic paint is a responsive material that absorbs ultraviolet energy and changes color according to the level of UV energy. The paint changes color and range of absorbent to reflective colors upon the exposure to UV light. The paint is typically colorless in the absence of light, but when UV rays of a certain wavelength hit the paint, its molecular structure switches to an active state, letting light of a certain wavelength to pass through. Okay. Electrochromic windows change transparency in response to a voltage, and when their voltage is removed, it reverts back to normal. The three main families of materials that change color when a voltage is applied are electrochromic materials, liquid crystals, and suspended particles. The voltage applied to the surface of the material starts a reversible chemical reaction which changes the color of the window. The goal of these smart windows is to reduce the heating and cooling requirements of a building, hence increasing energy efficiency and reducing energy demand. Okay, now vanadium dioxide thermochromic windows, they change their color and respond to heat. The vanadium dioxide has a monoclinic crystalline structure that has a reversible metal semiconductor transition at 68 degrees Celsius. Vanadium dioxide structure transitions to tetragonal crystalline structure when exposed to infrared light, which gives it better reflective properties, aiding in the reflection of solar radiation and reducing cooling needs. Now, the transduction system, an example of it is piezoelectric tiles. This piezoelectric tile is made by a company called PaveGen, and it produces electricity when it's swapped on. Now, phase-changing materials. There are three types of phase-changing materials. There are organic, inorganic, and eutectics. Organic can either be paraffin-based or non-paraffin-based. Their advantage is that they're chemically stable, they don't have segregation, they freeze without much supercooling, and they have a high heat of fusion, and they're recyclable. The disadvantages, however, they have low thermal conductivity, they're flammable, and they have low latent heat storage capacity. Now, the inorganic, they're hydrated salts. Their advantages are their high latent heat storage capacity, high thermal conductivity, low cost, and they're readily available, and they're non-flammable. And the disadvantages is that they expand a lot because they have a high change of volume and supercooling. And eutectics, the higher latent heat storage capacity is an advantage, and they have a sharp melting point. The disadvantage is that they're not widely available. Now, the use of PCMs could either be passive or active. The passive use of PCMs could be in walls, floors, and windows, and the integration of PCMs in walls such as drywall, wallboard, gypsum board, etc., can lead to a significant energy saving by absorbing heat and solar radiation in ways that typical walls cannot. Active applications of PCMs in cooling and heating systems could be the use in floor and ceilings, as well as the integration in double skin facade systems.
Recommendations for future enhancement for the smart building technologies is boosting the economic growth and providing more job opportunities in the energy field, raising awareness on smart building technologies and providing sufficient training from manufacturers, transformation of lending markets to focus more strongly on energy efficiency finance, delivering more sophisticated energy management, and providing high rates of space utilization. As a conclusion, energy-efficient buildings using smart technologies are the present, now, and the upcoming future. Smart materials and smart systems are integrated and operated as a whole system in smart buildings, and energy-efficient designers focused on new technology materials, such as nanotechnology and phase-changing systems. Also, energy systems are a large part of what will make a building smart, and so the energy system of a building must be the smart part, the smart system in the building. We need future enhancement in the energy sector because they are crucial for the expanding of smart building technologies. And smart building technologies are a must to implement in every buildings to save energy and to save costs. Thank you for listening. And do you have any questions?
Okay, thank you. So first, does anyone have questions before I start? Okay. Can you go please to slide 30?
Yes, of course. Yes.
It didn't appear yet. Slide 30.
30?
Yes,
Do you mean this? Okay.
yes, yes. Ahmad, can you please? No, the next one. 30. This is 20.
This?
30, the blue one. Yes.
Yeah.
Ahmad, can you please explain more the details of this?
It is in my part.
It's fine, but I can ask any of the participants.
Yeah, of course. I'm sorry.
Okay, Ahmad.
Yes, Professor.
Can you please explain for me the details of what is happening here?
Yes, so first we have the electricity generation and transmission to and from the grid. And the transmission goes into the grid services, into the energy management system, and back to the building, where they have panels integrated, and also the HVAC system, and all the components they communicate together, and they send back to the ESI, and the excess energy produced by the building goes back to the ESI and back to the transmission system to the generation.
Okay. Nagam, do you have something to add?
I don't really have something to add. I know he said everything.
Aya?
Yes, the whole point of this graph is to show how everything from the transmission to the renewable energy sources and the grid systems to the whole technologies, how they are all integrated together and work on the same IoT and the same cloud-based system, which is really fascinating.
Okay. Can you go please to slide 33? Nagam, can you talk for me please more about this panel?
Sorry, but I still don't see the screen.
Okay.
Second.
Now, do you see it now?
It's pixeled. I don't see any. I think it's because of my connection. Just let me connect to.
Can you zoom? You don't have the presentation, Nagam, on your computer?
Bala, yala, I have it. Which slide is it?
Slide 33.
Okay, just a second. Okay, just a second. I can't find the slides. Okay, so basically, I found it, Michelle. There are two sheets, and in between these two sheets, we have insulation and shatterproof FRP face, and then aluminum core, just to hold the thing together. And this helps in the self-cleaning properties, and it provides additional resistance to ultraviolet light and heat exposure.
Okay. Can you move please down with the slides, Aya? Aya, can you talk more about this system in slide 38?
Yeah. These piezoelectric tiles, they're tiles that people walk on. Yani they are used in mostly crowded places like malls or streets like Taqsim Street or streets that are crowded. And basically it's when someone is is crossing over, he's putting his leg on, it's creating a force. And في عنا two plates, a positive and negative plate, وفي البيزو electric material بالنص. فلما بيصير في عنا الفورس بيصير في عنا electric charges عم بيخلق voltage عنا. This voltage we could use later on أي شيء نحن فينا نستعمله applications but as a form of electricity. يعني these tiles are used to generate electricity. they would be very beneficial in crowded places لما عم يكون عنا steps all the time. فهيدا الشيء مثل فينا نعتبره free أو مثل kind of renewable energy إنه it's free from the steps تبعه العالم اللي عم يمشوا عليها.
Okay, thank you. Ahmed, anything to add?
I think she said everything, but كمان their technology it works by using force to make electromagnetic induction generators from vertically deformed material, and this is what creates the current to light whatever or give the electric output.
Okay, thank you, guys.
You're welcome.
Thank you.
I will send you another link to enter a new meeting to continue, okay?
Okay.